how an electric field is produced inside a circuit that maintains the current. On Friday, I'm going to do a review session. I'm going to cover different aspects of quiz number 2 and also a few problems on electric circuits. Okay, so let's get settled down. Alright, are we in a position to start now? So the question we would like to ask ourselves is, whenever there is current flowing through a conductor, an electric field exists. The electric field is parallel to the direction of the current density. Okay, the system is out of equilibrium. If the current is steady, the electric field is the same throughout the area, or maybe not. So this is something we would like to investigate. The other question we started off with is that the drift velocity is extremely small as compared to the thermal velocity of the electrons. So how in this world can electrons, the sea of electrons, flow from one point to another? And when we operate electricity in our homes, everything happens almost instantaneously. So how do we reconcile these concepts? That the drift velocity is extremely small, but a bulb glows up instantaneously. Now I would like you to pay attention to me. मैं यहाँ पे क्लास में खड़ा हूँ और कुछ बात कर रहा हूँ. We would like to start the class. Alright, so all of these concepts make sense when we understand what is electrical feedback. We've already seen electrical feedback in disguise, even though you don't recognize this as feedback. Suppose I have a metallic object, arbitrarily shaped. It's uncharged, so there is no charge, no net charge on any point on this volume. Now all of a sudden, two plates appear, which are the source of an electric field. So an electric field is produced all of a sudden at time t equals 0. So this electric field has a certain direction, of course. Suppose this is the direction of the electric field. It's produced at time t equals 0. Before time 0, the field doesn't exist. So this electric field is produced, of course, by a distribution of charges. मेरी आवाज़ ठीक आ रही है ना पीछे? कोई गूंज तो नहीं ना कर रहा? Now we already know that inside this metal, the electric field has to be 0 if there is no current flowing through the metal. So how is that electric field 0 maintained? It's maintained by the development of charges on the external surfaces of the body. Right? So where do these charges come from? These charges come from inside the volume of the metal. They're not imported from elsewhere. They're already there, intrinsically present inside the metal. And the entire, as soon as the sea of electrons, the mobile electrons, the free electrons inside the metal, which exist all the time, as soon as they see the external electric field, the sea of electrons would move with a certain drift velocity, because now we have an applied electric field, and the sea of electrons will move in such a way that the entire sea of electrons will shift towards the left. And when this happens, the sea of electrons would peak at this surface, and there will be a depletion of negative charge on the surface. And the net result is that this surface would acquire a positive charge on the surface, this surface would acquire a negative charge. And when these charges redistribute themselves in such a way that the internal electric field, the field inside the metal, E internal, is exactly equal to the applied field, inside this metal at every point, the net electric field inside the metal will be 0. Okay? So this is what is happening in the electrostatic condition. At time t equals 0, the electric field is imposed. The charges must redistribute themselves. It takes a finite amount of time to do that, even though the finite amount of time is extremely small, in nanoseconds or picoseconds or microseconds. And the charges redistribute themselves in such a way that the net electric field inside is 0. And whenever charges redistribute, the amount of time it takes for the electric field to appear is just the speed of light divided by the distance from the charges which are producing the electric field. So everything is happening instantaneously, and there are electrons everywhere inside the metal. So an electron need not travel from this point to this point to create a positive charge here. There are electrons here, there are electrons everywhere. It's just the entire sea of electrons that is gushing together, sloshing together, moving together, which creates this charge distribution, and it happens almost instantaneously. So this is an example of negative feedback. Electrical engineers will take an entire course on feedback and control, but this is probably your first introduction to feedback. An external field is imposed, the charges redistribute themselves in such a way that the net electric field opposes the external stimulus. So, and the net field inside this metal remains 0. So this is the concept of negative feedback. Feedback means a response is such that it opposes the stimulus, so that the original equilibrium condition is restored. So this is an example of feedback. We've already seen this example when we discuss electrostatics. Now the same concept of feedback applies in electrical circuits as well. Okay? Now let's take this concept a bit further. Suppose I have a wire, arbitrarily shaped, and I take some cross section of this wire, say A dash. Okay, it's a cross section of the wire, normal to the length of the wire. Now there is some current going into this cross section. Let's call this current I1. And suppose there is some current going out of this section, I2. Now remember that when we talk about currents, when I write A, it generally means a conventional current. Now if I1 is greater than I2, what's going to happen? What's going to happen at this plane A dash? Charge is going to? Charge को क्या होगा? Accumulate होता रहेगा, क्योंकि there is more charge per unit time coming in than going out. So with time the charge build up on this plane is going to increase. The charge is going to build up on this plane. Okay? So when charge is going to build up on this plane, so this plane acquires a positive charge. Alright? ठीक है? When I1 equals I2, there is no charge build up. Whatever charge comes in per unit time leaves in the same amount of time. So whatever charge has already been built up on this surface will remain there. I1 equals I2 does not mean there is no charge here. It means whatever charge has been built up, it remains there, it remains steady. So a steady current really means that whatever charges, if they exist at all along the conductor, they don't change with time. This is what steady current is. Okay? Now suppose we take this situation again, I1 is greater than I2. So more charge coming in per unit time, this plane acquires a positive charge. But there are continuously positive charges coming in because the conventional current is carrying positive charges. Now what this positive charge that is accumulating on the surface does to the incoming charges is that it impedes their flow. It stops their flow. Because it's already positively charged, the plane is already positively charged, there are more positive charges coming in. So it stops their flow. Okay? So the effect of this charge build up is that I1 starts decreasing. And the effect on I2 is that if these charges build up, it would push more positive charges away from the plane because of the repulsive effect, because of the Coulombic repulsion. So I1 will start dropping and I2 will start increasing. So this will start dropping, this will start increasing till balance is maintained again. And this process of charge build up will continue until I1 equals I2. So charge is continuously being built up, but the build up of charges is opposing the misbalance of the incoming and the outgoing current. And the build up of charges continues such that the incoming current eventually equals the outgoing current. So the incoming current goes down, the outgoing current goes up, eventually I1 becomes equal to I2. And when I1 becomes equal to I2, whatever charge that has been built up on the surface remains there. So this is another example of negative feedback. If somehow the incoming charge on this plane, the incoming current has gone up beyond I2, it will result in a build-up of charges which will counteract the unbalance of currents. And the build-up of charges will continue such that the incoming current will become equal to the outgoing current. So this is another example of negative feedback. Now I give you half a minute, since it's a logical argument, I give you half a minute to understand this and think about it on your own. पहले सोचो. हाँ जी, आपका सवाल. That remains there. So steady current means that, and uniform current means that whatever charges have been built up will remain there. Okay? जी. देखो, ये पॉजिटिव चार्ज प्लेन है, मेरे अंदर पॉजिटिव चार्ज लेके आ रहा है ना, कन्वेंशनल करंट. तो मैं खुद पॉजिटिव हूँ, मैं उसको रिपेल करूंगा. सो आई एम डिक्रीजिंग I1, द चार्ज दैट्स कमिंग इन, एंड आई एम इंक्रीजिंग द चार्ज दैट्स गोइंग आउट जस्ट बिकॉज ऑफ कूलॉम्बिक फोर्सेस. ओके, सो इवेंचुअली द equilibrium, dynamic equilibrium is achieved, or one can say that these currents become equal when the charge has been built up to such an extent that the negative feedback has made the currents balanced, perfectly balanced. That's why whenever you have a current that's coming in a wire, and then you have a node, and then you have two currents that are going out, I2 and I3. Steady state means that whatever charge has been built up, suppose some charge has been built up, it does not change with time. Okay? So if steady state has been achieved, then no charge can be built up or depleted at this node, and that can only happen when the current coming in equals the current that's going out. So the current coming in is I1, the current going out is I2, I3. So I1 must equal I2 plus I3. This is generally called the Kirchhoff's current law. Kirchhoff's current law. KCL. Okay. If steady state is to be maintained, no charge can build up at any point on the circuit. Or no charge, the charges that have been built up on the circuit will not change with time. They can neither increase, neither they will be depleted. Okay, so this is what is meant by steady current. Alright, now let's see what happens. Let's look at another example of negative feedback. Suppose I have a straight wire. Now for convenience I am talking about free electrons inside a metal. So this is the velocity, the drift velocity of electrons. Okay? So this is the drift velocity of electrons. The current density is in this direction, J, because I'm talking about negatively charged electrons. So this is the drift velocity, this is the current density. What's the direction of the electric field inside this conductor, which can maintain this current density? What's the direction of the electric field? Up top? Huh? Towards right? Why? No, it's negative. It must be parallel to J. So the electric field is pointing in this direction. This is the electric field. And remember the relationships: J equals sigma E, okay, V drift velocity equals some Q tau over M E, okay, and J is equal to sigma E, and this is also equal to Q N VD E. Okay, so J is proportional to the electric field. So these are relations we derived in the previous class. This quantity, that is the relationship between the drift velocity and the electric field, is also called mu, the mobility of the charge carriers. So since we're talking about negatively charged electrons making a current here, this is the velocity of the electrons, the direction from left to right. The electric field has to be in the opposite direction. It exists inside the conductor. The electric field is not zero inside the conductor, because a steady current does not mean equilibrium. If there is some electric field, there will be some drift velocity. If there is some drift velocity, this is QNVD. There is no E here. VD has an E. If there is some drift velocity, there is a current density. Okay? Acha. Now this electric field is parallel to the current density. It's also parallel to the velocity. So and electrons are flowing in the straight wire along the axis of the conductor. Suddenly, what we would like to do is we would like to take this current carrying conductor, pick it up from the hand and twist it. We twist the current carrying conductor. Still the current is going to flow. Nothing is going to change the current. We have only changed the geometry of the circuit. Now let's see what happens. The current density has to change its direction. The velocity of the electrons has to change. In this case, all the electrons, the sea of electrons was moving from left to right horizontally along the axis of the conductor. But here it must change. So what's going to happen here is that at the instant we've made this bend, the velocity of the electrons does not imagine that a change has been made. At the exact instant we have made this bend, the electron is still moving forward with the same horizontal velocity along the original axis of the conductor. Okay, so what's going to happen is that these electrons will be pushed into the wall of the conductor, into this wall of the conductor. Here they were not pushed into any wall of the conductor because they were moving along the axis. So at the instant we've made this bend, these electrons will hit against or push against the wall of the conductor, and they can't leave the surface of the conductor because of the work function of the metal. So they will accumulate at this kink, at this bend. Okay? So now you have a bend here that becomes relatively negatively charged, and there is a small positive charge that is created here because this region is depleted from electrons. The electrons are moving towards the bend. Now what this negative charge does, it activates a negative feedback mechanism. It will impede the flow of incoming electrons. Right? Because the electrons are negatively charged. This is a negatively charged charge that has accumulated on the surface of this conductor. It impedes the flow of electrons and it directs the electrons to go away. So the electrons will go away only by one mechanism. They will start changing their velocity. The direction of the velocity is going to change. Okay? So they will start changing their velocity. And this charge buildup will continue to the point that the velocity has changed its direction enough that it matches the new curved axis of this conductor. And all of this happens almost instantaneously, not in zero time, in a finite amount of time, over a period of nanoseconds. And you don't really perceive, you just think it's happened instantaneously. It takes a few microseconds or nanoseconds for this effect to occur, but the current then quickly changes its velocity until it becomes parallel to the axis of the conductor again. In fact, in the tutorial on Friday perhaps, I will demonstrate that if you talk about a high conductivity material like copper, if there is an excess charge of only one electron, it is sufficient to move a current of 1 ampere through a band of say 1 meters. Only minute charges are required here to make a large current bend its direction. And this is something you can calculate. How much charge is required? These charges that are created on the surface are really small. You can calculate those charges. I will give you an example in the tutorial. So the charges are minute. And the electric fields inside the conductor are really minute. So if you have a similar situation, a straight conductor, this electric field will be so small that it will be comparable to the field from a single electron at a distance of about 1 centimeters. So small a field. But these small fields, these electric fields are required for the current to flow. G.
So, but obviously we are changing the direction of, or we are accelerating because we are changing the velocity. Sir,
so at each point the electric field is also going to change. So the electric field was originally in this direction. Now the electric field is going to be in this direction, here it's going to be in this direction, here it's going to be in this direction.
So can we say that a conductor which there is a charge flowing and a conductor which has no charge flowing, it would require more, even a minutely more force to bend a conductor which is conducting.
So more mechanical force is required.
Bend it.
Yeah, but the forces you're talking, yeah, that's correct. But the forces you're talking about are minute. The electric force due to one electron at a distance of 1 centimeter is a minute force. Okay, this charge imbalance would be of the order of femtocoulombs, 10 to the minus 15 coulombs. But these small misbalance of charges is essential to have this negative feedback mechanism and to maintain electricity in our daily lives. This negative feedback maintains electricity in our daily lives. And remember, whenever the charge redistributes, the electric field propagates. The effect of the electric field propagates at the speed of light. So everything is happening almost instantaneously, even though the drift velocities are really small. Okay? So this is another example of negative feedback in which we considered a bent wire. Now let's look at what's happening inside electric circuits. Like a wire connected to a battery. Where are the electric fields coming from? ओके इसी बात पर हमने पिछले लेक्चर में कहानी खत्म की थी. Right, I need big blackboard here, so this is the positive terminal of a battery, and I'll explain what a battery really is. This is the negative terminal of the battery, and then I have a circuit. The circuit looks like the following. It's just a piece of wire connected with the terminals of the battery. Okay, and the circuit looks like this. This is a piece of wire connected to the two terminals of a battery. Okay, of course current is going to flow through this wire. small, large, we don't care, but a current is going to flow. Now what I would like to do, I would like to model this battery. Batteries are one of the most complicated things to understand in all of electrical engineering and all of electricity and magnetism. No good description can be found in textbooks. It's really a difficult concept. I will try to simplify this concept. I will try to present a model of a battery and how it works. Now the model that I'm going to draw for the battery looks like the following. So my model of a battery is the following. I have two plates and they are connected by a conveyor belt. ठीक है? ये conveyor belt एक मोटर है जो रोटेट कर रही है और ये belt from left to right it's moving. Okay? Just like what's happening in a Van de Graaff generator, there is a belt that's rolling from a bottom conductor to a top conductor. So this is my model of a battery. And what this conveyor belt does is that it picks up negative charge, electrons from this plate and transports it to this plate. So एक बेल्ट है वो इस प्लेट से ये वाली प्लेट है इससे एक नेगेटिव चार्ज उठाता है बेल्ट पे आता है वो बेल्ट मूव करती है और वो नेगेटिव चार्ज इस पे डिपॉजिट कर जाता है. ठीक है, तो एक नेगेटिव चार्ज एक इलेक्ट्रॉन इसके ऊपर गिरा ये ट्रांसपोर्ट हुआ और इसके ऊपर डिपॉजिट हो गया. तो वक्त के साथ साथ होगा ये कि इसके ऊपर पॉजिटिव चार्ज बिल्डअप हो जाएगा on this plate, right? The conveyor belt is trying to put more electrons on here, but the electric field is opposing it because it's already negatively charged. Suppose the electrons are being transferred from plate A to plate B with the velocity v. Okay? If the electrons also start leaving this plate with the velocity v, and they also start entering this plate with the velocity v, then it's possible that a constant charge is maintained on these plates. Correct? So the velocity of electrons coming into this plate is equal to the velocity of electrons going out of this plate. Okay? Which means that whatever charge has been appeared on this plate remains constant. So once the transients have gone off, once this opposing electric field is large enough, no more additional charge will be deposited on this. Whatever charge has been deposited earlier remains there. So this becomes the negative terminal of the battery and this becomes the positive terminal of the battery. Okay? So this acts now like a dipole. And now we have connected a wire with the two terminals of the battery. What we would like to do now is I use this pink marker for the electric field. Okay? This is the electric field. What I would like to do now is I mark few points. I mark a point here, 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 and here. I have marked these 1, 2, 3, 4, 5, 6 points on this circuit. Due to this electric dipole that has been created inside the battery because of the conveyor belt, I would like to mark the direction of the electric fields at the points that are marked with the cross. What's the direction of the electric field here?
Right side.
It's to the left. Okay? This is the direction of the electric field at this point. Okay? It's pointing towards the negative charged plate. Okay? What's the direction of the electric field here? Left or right? due to this dipole.
Right.
Right. And parallel to this conductor, right? I mean, this conductor is along the axis of, is parallel to the axis of this battery. Okay, let's suppose that. So this is the electric field here. Due to this separation of charges that has been created by the conveyor belt. That's what the battery is. What's the electric field here? It's again to the right. But what about the magnitude of this electric field as compared to this field? Smaller, because there is a 1 over r cube dependence. So there is an electric field here. Still pointing to the right, but smaller in magnitude to this. राइट पे ही होगी, करंट की बात नहीं हो रही है अभी बात हो रही है कि we are finding out the electric field due to the battery only, because we don't know the source of the electric field. This is one source we know. We know that the only charge distribution here is on the battery. अगर आप लेफ्ट कहोगे तो उसका सोर्स क्या है उस इलेक्ट्रिक फील्ड? We don't know. We will have to find that out. Okay, so the electric field due to the battery is in this direction. अच्छा, ये जो इलेक्ट्रिक फील्ड है इससे बड़ी होगी?
Yes.
ये सबसे बड़ी होगी, ठीक है, ये वेक्टर सबसे बड़ा है. Now what's the electric field here due to the battery alone? It's again to the right, but again smaller. Right? So this is 1 over r cube dependent. Here the electric field is large in this direction, and here the electric field is in this direction, right? From left to right. So now we have identified the direction of the electric fields. अच्छा, अब हम ये कर जी.
Sir, why are you taking the direction of the electric field to be in this direction due to the battery?
What else? What other source of charges do you have here?
No, I'm talking about the direction. Shouldn't it be towards the negative?
That's what we're going to reach at. The point that I would like to make here is that I have a circuit, I have a battery. The battery is just a separation of charges. I would like to, if the current is being produced due to some electric field, I would like to identify the source of the electric field. Now the only source that I have apparently is just the battery. ठीक है, उस बैटरी की वजह से क्या इलेक्ट्रिक फील्ड प्रोड्यूस होगी, मैं वो देखना चाह रहा हूं, और किस तरह मैं एक बहुत बड़े प्रॉब्लम में घुसने लगा हूं. देखो, now this is the direction of the electric field due to the battery alone. Okay, this is E due to the battery, because apparently that's the only source of charges we have in the circuit. Okay. Now, based upon this electric field, I would like to draw the currents, the velocities of the electrons, suppose. Okay, the velocity vectors. I know that the velocity vector has this relationship. If this is a negative charge, the velocity is equal proportional to minus the electric field. Okay, because I'm talking about electrons here. So if this is the electric field, the velocity vector of the electrons locally at this field, which is just the drift velocity of the sea of electrons, because that's the only average that is non-zero, is pointing in the opposite direction to the electric field. Okay, so now I'm using blue to denote the velocity of electrons. Okay, so this electric field, which is produced by this distribution of charges, dictates a velocity vector for the electrons in this direction. ठीक है, यहाँ पे velocity vector क्या होगा? Left होगा, और थोड़ा सा बड़ा होगा because the electric field is larger. और यहाँ पे क्या होगा? और बड़ा होगा, और यहाँ पे इस direction में होगा, and it will be really large. इधर इस डायरेक्शन में होगा, it will be really large. Now there are two problems. The first problem is that this velocity vector is in the correct direction, because when a current is flowing, when electrons are flowing, the sea of electrons is going from this plate to this plate. It's running in the clockwise direction. The sea of electrons is moving with the drift velocity in the clockwise direction. So this is correct. This direction is correct. This direction is correct. This direction is correct. This direction is correct. But good grief, this direction is incorrect. Totally incorrect. Because you know empirically and just by common sense that the electrons must have a velocity in this section of the wire that is going from left to right. Because the entire sea of electrons is moving like this. Correct? So this velocity vector has turned out to be in the wrong direction. ठीक है? ये गलत. There is some paradox here. Something wrong here with our reasoning. That we are returning, we get a velocity that is in the incorrect direction, that is opposite to the actual direction of flow of electrons. Okay? The other problem here is that these velocity vectors are not equal in length. So the velocity is changing at different sections of the wire. If this wire is brought even downwards, the electric field will go down, the velocity vector will go down. So the current is different in different sections of this wire. And this is totally incorrect. That's impossible. The current in this wire has to be uniform. So there are two problems. One is the problem of incorrect velocity directions. The other is the problem of incorrect velocity magnitudes. Now what's going to happen? Due to this charge separation, initially this is the only charge separation we have in the circuit. Okay? और कोई चार्जेस का सोर्स नहीं है. ये न्यूट्रल वायर्स ली थी आपने और अचानक ही वो कनेक्ट कर दिया बैटरी के साथ. और कोई चार्जेस का सोर्स नहीं है. इन चार्जेस को देख के जो इलेक्ट्रिक फील्ड्स आ रही जिसको मैंने पिंक में ड्रॉ किया, दे कैन नॉट डिस्क्राइब द एक्चुअल स्टेडी स्टेट करंट. So how do we describe the steady state current? Once again we look at knock at the door of electrical feedback, negative electrical feedback. See what's happening here. थोड़ा सा मैं इसको इससे जरा दूर बना दूंगा. Now this is one bend of the wire. This is another bend of the wire. You see, in this section of the wire, due to the geometry, there are electrons coming in from the bottom and electrons coming in from the top. This becomes like a sink of electrons. So the electrons coming in from the bottom and electrons coming in from the top. So what will happen to this section of the wire? It will accumulate negative charge. So this section of the bend will accumulate negative charge all on the surface. And what's going to happen to this section? It's going to accumulate positive charge because on the top electrons are moving away and on the bottom electrons are also moving away. So it's being depleted of the sea of electrons. So the sea of electrons goes away from here with the drift velocity. The local, which depends on the field locally in this region. So this bend acquires a positive charge. Now what's going to happen? Now I would like you to think how these separation of local charges, positive and negative charges, can affect a negative feedback. What's going to happen? Just think about it. There's a positive charge here and a negative charge here. How will it change the electric field in this section of wire? Just think about it and I will ask you in about a minute what's going to happen. How is negative feedback going to work here? Because the problematic section for the time being is this section. Velocity यहाँ पे गलत direction में है. So we have to rectify it. So how will negative feedback help us? Think about it and then I'll ask you. आपको समझ आया क्या होगा अब?
वो नेगेटिव चार्जेस जो बिल्डअप हुआ है वो इलेक्ट्रॉन्स को उस डायरेक्शन में पुश कर रहे हैं।
तो फील्ड की डायरेक्शन को वेलोसिटी डायरेक्शन चेंज हो जाएगी,
एक नई इलेक्ट्रिक फील्ड प्रोड्यूस हो रही है बैंड की वजह से, है ना?
तो उसकी वजह से इलेक्ट्रॉन्स आगे उस डायरेक्शन में चले
तो न्यू इलेक्ट्रिक फील्ड की डायरेक्शन
ऑपोजिट है. शाबाश. So what we've seen here is due to the geometry of the circuit. Okay? Charges accumulate here. Opposite charges accumulate here. So there is a charge gradient. Now this charge gradient produces a new electric field. It starts creating a new electric field between this point of the wire and this point of the wire. Now I denote in green the electric field due to the, say, local charges. Okay? Charges that have been built up on different sections of the wire. Okay? इसको मैं green से जाहिर कर रहा हूँ. अब इस section of wire में मैं अभी consider कर रहा हूँ. The direction of electric field is pointing in this direction, right? Now the net electric field in this section will decrease. This was the original due to the battery. This is due to the band. More charges are deposited here. This electric field will keep on growing. Okay, nothing is going to happen to this electric field because it's at the same distance from the battery, and the battery के ऊपर चार्जेस ना बढ़ रहे हैं ना कम हो रहे हैं. ठीक है? तो अब वक्त के साथ जो चार्ज बिल्डअप होता जा रहा है, ये इलेक्ट्रिक फील्ड बढ़ती जा रही है until we reach a position when the net electric field in this region. Okay, now which color do I use? I use yellow. In this region, I would like to draw the net electric field. So this electric field, this charge will keep on building. उतनी देर तक बढ़ता रहेगा जब तक इस ग्रीन वेक्टर और पिंक वेक्टर का रिजल्टेंट gives me a net electric field in this direction. And the magnitude of this electric field is such that it gives rise to a velocity which is in this direction. Blue. So this is the principle of feedback that is at work, negative feedback. That is, instantaneously, in a very short span of time, charges are locally built up on this region. These charges that are built up in this section of the wire don't come from the battery, because charges are everywhere. The sea of electrons is everywhere inside the metal. They are readily available in this locality. So the sea of electron moves with few millimeters per second depending upon the electric fields, and it readjusts itself in such a way that this region becomes positively charged, this region becomes negatively charged, and opposing electric field starts building up, negative feedback. And this green field builds up to an extent that the net electric field represented in yellow now points in the correct direction. And it builds up to an extent that the velocity vector is also of the correct magnitude. And all of these net electric fields will build up to an extent. So the net electric field in this region, due to these charge redistributions, due to the negative feedback, is going to happen everywhere on this circuit, at all bends, everywhere. Okay, so the net electric field here will be in this direction. The net electric field here will be in this direction. The net electric field here will be in this direction. And the net velocity vectors will all be in the correct direction because of this negative feedback mechanism. And the net result is that all along the length of this conductor, local surface charges start appearing. Okay? Now let me give you a simple example for that, and then I will come back to this example. ठीक है? Negative feedback की वजह से कंडक्टर की सरफेस पे नए नए चार्जेस अपीयर हो रहे हैं, और वो चार्जेस इस तरह डिस्ट्रीब्यूट हो रहे हैं कि उनकी वजह से जो नेट इलेक्ट्रिक फील्ड बन रही है that is of the correct direction, of the correct magnitude, it's uniform across the length of this uniform wire, which will give equal magnitude velocity vectors. Now let me give you a simpler example. ठीक है, फिर हम इसके दोबारा वापस आएंगे. देखिए ये तरीका इलेक्ट्रिक सर्किट्स को देखने का आपकी किताब में नहीं है ऐसे. And most of the textbooks don't discuss electric currents in this manner. But this makes a beautiful connection between electric fields and currents. Okay. A simple circuit. Suppose this is negatively charged terminal of the battery. Okay. Now we already know that electrons are going to flow from this negative terminal in the clockwise fashion. They're going to come here and then they will be transported by the conveyor belt. And the velocity of electrons, the speed of electrons throughout this circuit is going to be the same. Because the speed determines the current. The current is uniform throughout this wire. So the speed of the electron has to be same here, everywhere. So this is something we know. So if I plot the vectors for this drift velocity of the electron, the velocity here is going to point in this direction, right? The velocity here is going to point in this direction along the axis in steady state, by the way. मैं अब steady state पे diagram बना रहा हूँ. It's going to point in this direction, right? Here it's going to point in this direction. Here it's going to point in this direction, in this direction. So this is the drift velocity vector along the length of the circuit. ठीक है, blue से मैं जाहिर कर रहा हूँ. I'm sticking to my coloring scheme. Okay, and all of these vectors have the same length because the current is uniform across the length of the circuit. Now, corresponding to this velocity, there has to be an electric field locally. Look at this relationship. And this is the net electric field created from the battery and the surface charges. Okay? Now, if I want to draw the electric field, what's the electric field here? This direction. What's the electric field here? U. इस तरह. ठीक है, यहाँ पे इलेक्ट्रिक फील्ड कैसे होगी? इस डायरेक्शन में क्या होगी? डाउनवर्ड्स. इस डायरेक्शन में डाउनवर्ड्स, leftwards, sorry. Here the electric field through this battery is going to point in this direction, right? Okay? And the velocity here is parallel to the electric field. It's in the same direction because it's a battery. I will explain that because there's an EMF here. The potential change is different. Here the potential change is negative. Here the potential change is positive. Okay? Now this yellow represents the net electric field at different points on the wire. Now where is this electric field coming from? This electric field cannot be explained by the battery alone. We've already seen that. Okay? It cannot be explained by the battery alone. Because if we were to consider the battery alone, the electric field here would point in some direction which is given by, it will be pointing in some direction like this, away from these negative charges. This is the electric field due to the battery alone at this point. Okay, due to the dipole. So, but the electric field can't point in this direction. The electric field has to point in this yellow direction opposite to the direction of the drift velocity of the electrons. So this electric field is predominantly produced by surface charges that develop along the length of this wire. Now we would like to draw a pattern of the surface charges which produce such an electric field. Okay? सवाल समझ आ रहा है? We're going logically. हम बहुत logically चल रहे हैं. हमने ये कहा कि battery alone cannot produce the distribution of electric field along the conductor that gives us a uniform steady current along the conductor. So we know that the velocity vectors have to point in this direction along the sections of the conductor. Okay? Which means that we can, looking at the current density, we can predict what the direction of the electric field must be. So the electric field must be pointing in these yellow directions. Where are those electric fields coming from? Those electric fields can come from the battery, and they will come from this locally developed surface charges. The contribution of the battery is really small because there is a 1 over r cube dependence. You move away from the battery, the effect of the dipole just vanishes off. So it's predominantly the surface charges that are developed on these surfaces of the conductor all along the length of the circuit that can produce such an electric field. Let's see how those surface charges look like. What are the pattern of those surface charges? एक सवाल था जी कौन सी? अगर सिर्फ बैटरी को देखें तो इलेक्ट्रिक फील्ड की ये डायरेक्शन है टुवर्ड्स द नेगेटिव प्लेट. सॉरी, और कोई सवाल?
Are you considering electrons or conventional current?
किस चीज के लिए? Blue is the drift velocity of the electrons. Pink is just the electric field due to the battery. I mean, electric field does not have to do anything with kind of charge carriers. ठीक है? अब हमें इलेक्ट्रिक फील्ड वेक्टर की डायरेक्शन पता चल गई जी. हाँ. Sorry? There is conveyor belt. This is what the model of the battery is. There is a conveyor belt that is transferring charges from this point to this point. Now, how is it physically done? I'll explain that. Okay, when I talk about EMF. This is just a model of a battery, an equivalent model of a battery that helps us understand what happens inside a battery. Now, for ease of understanding, I'm just erasing this pink arrow so that you can understand what's going on. Now the yellows represent the direction of the net electric fields. The electric field here is in this direction, the electric field here is in this direction. The electric field here is in this direction. Now what kind of surface charges can create such an electric field? Right? The electric field has to come from somewhere, it's not coming from the battery. The effect of the battery is really small. So this electric field that is locally developed along the length of the conductor has to come from somewhere. It's only coming from the surface charges that are developed, like the charges that we have drawn here, right? Because these charges are producing this electric field. Okay? So if I look at the electric fields, I need to know distribution of surface charge along this conductor. Now what kind of surface charge distribution can produce this pattern of the electric field? देखो, अगर इलेक्ट्रिक फील्ड है यहाँ इस डायरेक्शन में, तो इस सेक्शन में चार्ज कैसे डिस्ट्रीब्यूट होगा? There is more positive here, less positive here, okay, or more negative here, less negative here. ठीक है? So the electric field here is in this direction. So there is less negative here, more negative here. So along the length of the conductor, the negative charge becomes diluted. So if I draw a rough pattern of how the surface charges are distributed along the surface, the rough pattern will look like the follows. There are negative charges here. Okay, अब मैं yellow ही इस्तेमाल करता हूँ. Negative charges here. A high density of negative charges. Okay? and then the negative charges get diluter and diluter. Okay, यहाँ पे there are few negative charges, यहाँ पे ज़्यादा हैं, फिर आहिस्ता आहिस्ता कम हो रहे हैं, ठीक है? So it becomes diluter and diluter. At this point, there is a dilute negative charge, there is a dilute positive charge here. Then the concentration of positive charges slightly increases. Okay? Keeps on increasing on the surface. Finally, you have the highest concentration of positive charges near the positive terminals of the battery. So if I call this point A, B, C, D, E, okay, and if I were to plot the surface charge density on the conductor along the length of, so this is B, C, D, E, and A, right? So what is happening is that from B to C, B has the most negative charge. From B to C the charge gets diluted, and at D it just goes to 0. The net charge here on the surface is 0. So from B to D I go like this, and I am plotting the surface charges on the conductor. And from D it goes up again, and the charge becomes more concentrated. So the surface charge goes up and it reaches its maximum at A. So this is how the surface charge varies along the length of the circuit. Okay? So it's a constant gradient because this is a simple circuit. Constant gradient, more negative charge here, the negative charge gets diluted. And the charge concentration is such that it produces the correct electric field. And resultantly the correct electric current all throughout the conductor. And what do these surface charges look like? These charges are not produced inside the conductor, they are produced on the surface of the conductor. Suppose I have a section of wire. दो तीन चार पाँच छः सात आठ. Alright, now I've drawn a conductor in the form of a tube. On the surface there is a ring of charge. Right, so this is a surface charge density. Here there is also some charge, but the charge here is diluted. I'm talking about positive charge. So along the length of the conductor, say at the middle point, what direction would the electric field point in? From left to right or from right to left? From left to right. So inside the conductor, in the interior of the conductor, there is going to be an electric field pointing in this direction. Okay? So if I draw another situation in which I have positive charge here, 3, 4, 5, 6, 7, 8, and here I have 4 negative charges. Will still an electric field act here? Will there be an electric field here in the interior of the conductor? Yes. And what direction? From left to right. And what about the magnitude as compared to this? It will be much greater. Because the gradient in the charge is much greater. So the larger gradient in the charge creates a stronger field. So here all along the length of the conductor there is a gradient of charge. Gradient का मतलब तब्दीली है चार्ज में, यहाँ चार्ज ज़्यादा है कम है, उसकी वजह से इलेक्ट्रिक फील्ड्स डेवलप हो रही है. or the electric field has to be constant throughout the length. So the gradient is constant throughout the length of the conductor. If I have a situation like this, in which I take the conductor, I have lots of positive charge here. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 16. I have lots of positive charge here. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 16. What's the electric field at the center? 0. Even though the surface charge is large, there is no charge gradient. There is no charge gradient, there is no potential difference between this point and this point, and there is no electric field, and a current cannot flow through such a conductor. Okay? So now let's look at this circuit again. The yellow vectors determine the correct electric fields, which must be created by some local charges that are developed along the surface of the conductor throughout the length of the circuit. Okay? So if the electric field here is pointing in this direction, in this direction here, there has to be a distribution of charge. So the electric field is pointing in this direction, which means that this is more positive. This is more positive, then this is more negative. So, if this becomes negatively charged, there is a higher concentration of negative charge here as compared to this point, because then the electric field point in this direction. Here the electric field is pointing in this direction, so the negative charge concentration here will be still higher. Right? And it will be still higher at the terminal of the battery. So there is a distribution of charge all along the length of the circuit such that the distribution produces an electric field at each point of the circuit which gives us the correct current density. The current density is uniform across the length. Now I would not like to take questions, rather I would like to ask someone to summarize this in a minute. Can anyone summarize this for me? What's happening? What's the logic of the argument? How is the argument flowing here? What causes an electric current inside this circuit? Can anyone volunteer to summarize this? क्या है ट्रेन ऑफ आर्ग्यूमेंट्स, क्या है थॉट्स हमारी किस तरह डेवलप हुई हैं? कोई वॉलंटियर कर सकता है? आप कर सकते हो? बोल।
So you initially explained
ब्रीफ रखना है।
You initially explained that we have a model of the battery which has two plates connected by a model of a conveyor belt which is carrying a charge from one plate to the other. This buildup of charges on both plates causes an electric field to appear on both plates, which impedes the flow of the conveyor belt. So we have a constant speed Vd, which is the speed of the charges going from the positive plate to the negative plate, and when we connect the two plates together by a conductor, which is the wire, there exists a flow of charge. Actually, electric field is created within this conductor, which causes the negative charge from one plate to flow through the conductor to the positive plate. This is how the electric field is induced within the conductor also, because it acts as a dipole, the battery which you have shown above, which is what I remember.
So my question is, any better? That's good. Thank you. Any better idea? Any better train of thought? कोई और? हाँ.
So I have a different model.
Okay. Please come over.
Assalamu alaikum. It's not. This wasn't a very important question for me. That charges इलेक्ट्रिक फील्ड से किस तरह हो रहा है। बिकॉज क्या अगर हम एक वैक्यूम को सोचें, एक ट्यूब है और उसके एक साइड पे एयर पुश हो रही है, एक साइड पे एयर सक इन हो रही है, तो क्या हमने सोचा कि अगर ट्यूब बहुत लंबी हो तो वैक्यूम का प्रेशर तो उसके मिडल में कभी पहुंचेगा ही नहीं, तो फिर कैसे चार्जेस फ्लो हो रहे हैं। या अगर एक कन्वेयर बेल्ट हो, एक इलास्टिक हो, उसको एक साइड से पुश किया जा रहा है, तो क्या हमने कभी सोचा उसके मिडल में तो फोर्स पहुंच ही नहीं रही। तो वो इसलिए जिस तरह हम उसको एक्सेप्ट कर लेते हैं एज इज कि हर इंडिविजुअल पार्टिकल जो है वो अपने साथ जुड़ा हुआ है, तो जैसे मैं एक को टारगेट करूंगा तो इंस्टेंटेनियसली भी नहीं, खैर ओवर टाइम वो चीज दूसरे पार्टिकल को, वही अगला पार्टिकल जो है वो सक इन कर लेगा। बिल्कुल इसी तरह इंस्टेड ऑफ थिंकिंग के इस बैटरी की इलेक्ट्रिक फील्ड यहाँ पर पहुंच रही है और वो कॉज कर रही है, इसको हम ओवर टाइम देख सकते हैं कि अगर यहाँ से एक इलेक्ट्रॉन जो है वो पुश अवे हुआ है और यहाँ पे एक इलेक्ट्रॉन पुश इन हुआ है, तो उसका एक इक्विलिब्रियम सेट था अपने साथ वाले इलेक्ट्रॉन के साथ। हम उस वक्त क्या सोच रहे हैं कि वो किस तरह सेटअप है, वो है एक खास एक एवरेज डिस्टेंस पे एक दूसरे इलेक्ट्रॉन से। जैसे ही वो इक्विलिब्रियम डिस्टर्ब होगा, वो उसी इंस्टेंटेनियस जिसको हम स्पीड ऑफ लाइट कहते हैं उससे वो हो जाएगा। तो बस समझ
ये बिल्कुल गलत है, क्योंकि इलेक्ट्रॉन जब कंडक्टर के अंदर फ्लो हो रहा है, an electron cannot exert a force on a neighboring electron. One electron, I mean this is incorrect. उसकी फोर्स एक से दूसरे पे ट्रांसमिट हो रही है।
एक पोर्शन ऑफ कंडक्टर के अंदर कम होगा चार्ज, तो उसको फिर वहाँ पर पोटेंशियल डिफरेंस क्रिएट होगा और वो पोटेंशियल डिफरेंस ग्रेजुअली एक्सटेंड करेगा।
लेकिन ये बिल्कुल नहीं हुआ कि one electron in a wire cannot push on another electron. It's not an electron that is exerting, it's not a chain of coupled oscillators that one oscillator is pushing on a neighboring electron. You see, my train of argument is really simple. I know that a constant current, a steady current in steady state, uniform throughout this wire, has to flow. That requires a uniform electric field parallel to the conductor. Okay? Where is that electric field coming from? That electric field cannot come from the battery, from the dipole. Because even if you are far away from the battery, where the electric field of the battery doesn't reach, there is still a current. So that electric field comes from charges that are developed on the surface. And those charges are developed by local negative feedback mechanisms. Okay? And the negative feedback acts in a way that the electric field is constant throughout the wire. Okay? Its first charges are developed and they produce the electric field, which produce a current density. But it's difficult for us as human beings to find out the pattern of charges. We work backwards. We know that the electric current is constant, therefore the electric field must be constant in this wire, and such an electric field can be produced by such a distribution of charges. Alright, now one really important point. If I have, and I'm going to finish off with this point. I have a battery. Conveyor belt, negative charged plate, alright, now there is a gap here. I have not connected the battery, I have not closed the circuit. There is an air gap. Suppose the resistance is infinity. Will current flow through the circuit? Only talking about DC. Will current flow through this circuit? क्या current flow करेगा? नहीं करेगा. ठीक है? So when there is no current, what about the electric field inside this conductor? Electric field क्या होगी? Electric field होगी या नहीं होगी? इलेक्ट्रिक फील्ड होगी या नहीं होगी? जीरो होगी, क्योंकि इलेक्ट्रिक फील्ड होगी तो वेलोसिटी भी होगी इलेक्ट्रॉन्स की, फिर करंट भी होगा. If the current is zero, which you declared it's zero, then the electric field inside the conductor is zero. It's an electrostatic conduction. There's no current, so the electric field inside is zero, and the electric field here is zero. But this is negatively charged, and this is one continuous conductor. ठीक है, ये भी कंडक्टर है, ये सारा भी कंडक्टर है, ये भी कंडक्टर है, ये भी कंडक्टर है. This is positively charged. So will there be any charge on the surface of this conductor? आप बताओ, will there be any charge on the surface of a conductor? और वो surface charge density क्या होगी? Will it be uniform? It should be uniform? No. If it's not uniform, then there's going to be an electric field. If the electric field is zero, then the surface charge on this wire should be constant. There is some surface charge. The charge on this battery, it will just distribute itself on the surface of this conductor, and all throughout the length of this conductor, the surface charge is going to be constant. Here the surface charge is going to be constant, positive. Only this constant surface charge density can give rise to a situation such that the electric field inside the conductor is zero. So before we have connected this circuit, the electric surface charge is evenly distributed. By the way, this surface charge is really small. 1 meter length, it's about 5 volts. It's an extremely small surface charge, but it's there. So this constant surface charge on this conductor will necessitate that the electric field is zero. In the next lecture, we'll start off by our lecture by seeing what happens when we break this gap, when these connectors connect. How does the electric field change all of a sudden? Alright, thank you very much.